Hello, Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another exciting science session. And today we are talking about mixtures and solutions. So let's go. Right. Let's have a look. So we are going to be distinguishing between different types of mixtures, solutions, colloids, and suspensions. We're going to be talking about different ways of separating mixtures. We are going to be talking about these words over here: mixtures, colloids, suspensions, solutions, solvents, solutes, and solubility. And by the end of today, hopefully you'll know what these words mean and how to use them and where to use them. Right, let's have a look. So the first thing we need to talk about is what is a mixture. Well, we know what a compound is. So remember, a compound is when two or more elements are chemically bonded together, either through covalent bonding or ionic bonding, right? Compounds are not very easy to separate. Okay, so once two or more elements are bonded together, as in the case of sodium chloride, for example, we can separate them, but of course, compounds are not very easy to separate. There are different ways, such as heat, for example, in a process called thermal decomposition, means breaking up using heat. But of course, that requires a lot of heat, and sometimes it requires special instruments and special lab instruments to break up a compound. Compounds are not always very easy to break up. Why? Well, because elements don't want to break up, they want to stay together. Remember, elements would like to be stable, and in order for them to be stable, they need to either share electrons or gain electrons in order to satisfy that octet rule. And so once they're together, and once they're satisfied, and once they have enough electrons surrounding them, they really don't want to separate. So compounds are not so easy to separate. Thank God that's not the case with mixtures. So mixtures are not so hard to separate. Well, mixtures are not compounds, you see. Mixtures are two or more elements or compounds, just two more substances, either elements, compounds, or whatever, that are mixed together. They are not chemically bonded. We can separate them quite easily using different methods. Okay? So compounds are chemically bonded, whereas mixtures are not chemically bonded. Compounds form new substances that usually don't share the same properties as the elements that make them up. For example, sodium is a metal, chlorine is a gas, sodium chloride is salt, and it's different to both the metal and the gas. Whereas mixtures share the properties of the elements that make them up, or share the properties of the compounds that make them up. Okay, so for example, just really quick, if I mix salt and sugar and you have a taste of it, it's going to taste salty and sweet because it's both salt and sugar, whereas a compound would be quite different. Right, so now that we know the basics, we just ran through it real quick, let's talk about the different mixtures. So now we're going to focus on the mixtures, yeah? Forget compounds for a second, we're going to focus on mixtures. Mixtures can either be homogeneous or heterogeneous. And what is the difference between them? Well, in short, homogeneous is one color, one blend, uniform throughout. The word homo means same, homogeneous means same throughout. So things like milk, for example. Milk, the same throughout. That is homogeneous. Whereas things that are heterogeneous, things that are separate, that are different. So here I've got a mixture of oil, cumin seeds, and water. And that is heterogeneous, right? Because it's different. It's distinctly different to my eyes. Things that are like, for example, another example would be a fruit salad. A fruit salad, is it different throughout or is it uniform throughout? It's different throughout. We've got different colors, we've got different textures, we've got different materials. A fruit salad is heterogeneous. Right. What about lentil soup? Lentil soup, it's the same uniform throughout, especially if it's blended. That is kind of homogeneous, right? What about sand mixed with shells? That's heterogeneous. What about seawater? It looks the same throughout. That is homogeneous, right? So water with, let's say for example, water with dissolved solids in it, like magnesium or sodium. That is homogeneous. What about apple juice? Homogeneous, okay? Because it's the same throughout. So one more time, heterogeneous means you can see it with your eyes. It's different. There's different things in there. And homogeneous looks the same color, looks the same throughout. So in this example, the seawater is homogeneous, while the sand mixed in with the shells is heterogeneous. Okay? Let's keep going. Right, and here is another example. So I've got milk, sugar, and coffee. And if I mix them together and I mix them really well, this is what I get. I get a beautiful mixture of my morning coffee. Now, as you can see, it's the same color throughout. Beautiful, same color throughout. What does that mean? It means it's homogeneous. It's the same color throughout. What about this guy over here? That is heterogeneous. Why is that? Different colors, different textures, lumpy. It's heterogeneous. I can tell just by looking at it. It is heterogeneous, right? So that is a very quick example right there. More examples. Homogeneous, things that blend in, look the same. Coffee, Vimto, the air looks the same throughout. You don't look at the air and see like yellow patches and orange patches. That would be weird. Well, I guess you can sometimes if there's smoke, but then it becomes heterogeneous. Now, normally the air is a homogeneous mixture of nitrogen, oxygen, carbon dioxide, just a wee bit, and argon, xenon, helium, all sorts of gases, right? But it's a homogeneous mixture because it all blends in together and it looks nice and clear. It looks the same throughout. And if I take any sample, it's exactly the same. The distribution of those gases is the same. So it's a homogeneous mixture. Vimto is the same. That's a homogeneous mixture. Coffee, well, we just explained the coffee. I'm going to come back to these two, okay? I'll come back to these two. But natural gas is also a homogeneous mixture. Vinegar, this is what I actually have over here, by the way. That's vinegar. Ooh, smells pungent. Vinegar is a homogeneous mixture. And blood is a homogeneous mixture because it looks the same throughout. But what about this business with brass and steel? Well, it just so happens that I've got a bit of steel over here. Now, why is this homogeneous? Why? Well, if you look carefully at this, right, you can see that it looks the same throughout. But then again, is this a mixture? Well, it turns out we've got covalent compounds. Remember when we're doing covalent compounds? They are between nonmetal and nonmetal. Nonmetal and nonmetal makes a covalent compound. They share electrons. What about a metal? A metal and a nonmetal. What does that do? A metal and a nonmetal, they form ionic compound. The metal donates electrons, the nonmetal accepts electrons, it forms an ionic compound. What about a metal and a metal? Well, it turns out metals and metals don't exactly like to bond together. They don't form compounds, but instead, what you can do is you can heat the metals together at very high temperatures, melt them together, mix them together, and that's called an alloy, okay? And an alloy is a mixture, and it's a homogeneous mixture. Look, it looks the same throughout. You wouldn't be able to tell that this is a mixture of zinc, iron, and carbon, but that's what this is. Zinc, iron, and carbon mixed together very, very well throughout. It looks the same color. See, it looks just like one color, and it's beautiful. Now, why would they mix metals together? That's a long story, but in short, you get the properties of different metals, and you avoid things like corrosion and rust. So it's a good idea, okay? But that's not the topic of today. The topic of today is mixtures, and brass and steel are examples of mixtures when you mix different metals together, and they are homogeneous because it looks the same throughout. Okay? What about heterogeneous mixtures? You see the cookies? You see the chocolate chips? That's heterogeneous. Obvious, really. Pizza's a heterogeneous mixture. Fruit salads, normal salad, sandwich, soda with ice. Soda with ice. Now, the soda itself can be homogeneous, but the soda with the ice is heterogeneous. Let's keep going. Okay, another thing that can help us differentiate between solutions, colloids, and suspensions. Now, here's the deal. Solutions. Well, actually, before I get into that, I think we need to talk about them. We haven't actually talked about them, have we? Right. Let's have a look. So, what are solutions, colloids, and suspensions? Well, it turns out mixtures, okay, can either be one of the three. Can either be solutions, colloids, or suspensions. What does that mean? Well, if I have something like this, where it's transparent, you can see through it, or something like this, Like this bottle of water with salt in it. Now this is salt water. This is a homogeneous mixture. But also, it is also something else. It's a solution. Why is it a solution? Well, a solution is when you have something dissolved in something else, okay? And you can't see it anymore. It's dissolved, it disappeared, and it's transparent. So this is an example of a solution, and this is an example of a solution, okay? And if I show you using my laser, okay, what I can do is I can actually pass light through it, okay? And you can see that light passes through it. You can actually see the light, okay? Light passes through it. What about this one here? Is it a solution? Well, let's see. Does light pass through it? Yes, it does. You can see the light passing through it, and it makes this beautiful effect. Let's switch off the light for a second. Whoa. That's cool, huh? So this is a solution. Right. What about the next one then? Colloid. What is a colloid? A colloid, unlike a solution, well, it's the same throughout. So a solution is the same throughout. A colloid looks the same throughout as well, but it's not transparent. It doesn't allow light to go through. What's a classic example of a colloid? A classic example of a colloid is good old milk. Okay, now what happens if I get a laser pointer through it? Can you actually see it? You can't see it. It doesn't come out the other end very well. Okay, and even if I switch the light off, okay, you can't see it passing through. And I'm trying very hard to make it go through, but it just won't go through. Now, why is that? As you can see from the picture, it has more particles in it. They're not as small, they're not dissolved, so it doesn't allow things to go through. And finally, a suspension. Now, I've got one example of a suspension over here, but a suspension can be a mixture of sand and water, for example. Why? What does the word suspension mean? Suspension means they separate after a while. So even if you mix them together, like mud and water, or sand and water, and you mix it, you shake it, what's going to happen is it's going to get cloudy. But then if you leave it for a while, it's going to settle. The sand will settle at the bottom, and the water will settle on top. Why? Because they are suspended from each other. They suspend. They separate from each other. Another example is oil and water, which is what I have over here. If you can see, the oil and the water just simply don't mix. And even if I try to make them mix, like I'm going to get something right now, and I'm going to try and mix them together. So I'm going to try and mix them. Here we go. Mix, 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 mix. Okay, still mixing. Now what's going to happen? As soon as I stop mixing, you can see it goes back to suspension and separation. And that is what a suspension is. A suspension is, doesn't matter how hard I mix, it's still going to go back after I stop mixing. So that is a suspension. So a suspension is an example of something that is going to separate. And those are the three different types. Solution is always clear. Things like apple juice, things like vinegar, things like water with sugar in it or salt in it. That is a solution. Clear. I can pass a light through it. I can see through it. Right? It's the same throughout. It's uniform. It's homogeneous. It's all the same. Now, what happens with colloids? Colloids are homogeneous somewhat, but they're not transparent, or they're not as transparent as solutions. So they don't allow light to pass through very well. Now, not all colloids are homogeneous. So if we're talking about milk, for example, milk, generally speaking, is heterogeneous because if you leave it for a while, believe it or not, if you leave milk, especially full fat milk, for a while, it will separate. It's got fat in it. So the fat layer will go on top and the milk will settle at the bottom. Okay? Now, if you take skim milk, which is fat-free milk, that is homogeneous. But if you take full fat milk, it's actually heterogeneous because it's two different things in there. So it's not black and white. Like sometimes things can be more than one thing depending on what they are. But generally speaking, the rule is this. If it's uniform throughout, it's homogeneous. If it's not uniform throughout and I can tell the difference with my eyes, it's heterogeneous. And if it's clear, then it's solution. If it's not clear, but it still looks like the same color, then it's a colloid. Another example of a colloid is that lentil soup I was telling you about. And if it's a suspension, then it means it's going to separate and go into two distinct um, layers. Okay, so let's keep going. I was talking about a solution earlier. What is a solution? A solution is a solvent, such as water, with something dissolved in it, like a salt or sugar. Once you dissolve the sugar in the water, or once you dissolve the juice in the water, or the tang in the water, or the sugar, salt, whatever you want to dissolve in it, it becomes a solution. So a solution is a mixture of solute and solvent. Solute being the solid that's dissolved in the solvent. Okay? And there are different ways of separating mixtures. So let's talk about separating mixtures. So you can separate mixtures using magnets, for example. Magnets are beautiful because magnets, for example, attract things like metals. So here I've got a metal, I've got a map of Africa, and I've got a metal here, and the magnets can separate the metals from the non-metals, right? So that's an easy way of separating, say, sand from iron filings or whatever. Another way of separating things or mixtures is using a hot plate. So how do I do that? Well, you see, if salt is dissolved in water, as in what I have over here, and if I want to get the salt back, how do I get the salt back? I can heat it. I can heat the water will evaporate, and then the salt will crystallize or remain behind. Okay, and that's actually essentially how a desalination plant works, like the ones we have here in Kuwait. So if I want to desalinate the seawater, that means remove the salt from the seawater and make it fresh. Essentially, I can then use it to shower and clean and even drink. What I need to do is remove the salt. How do I remove the salt? One easy way to do that is by heating the water. If I heat the water and then cool it, the water will condensate, will turn from gas to liquid, and then the salt will remain behind as crystals, right? So that's called desalination. So another way of removing things is through using a hot plate. And finally, I can simply filter it. So if I use a filter, I can remove things that are not dissolved in the water, things that are solid, things like sand. Okay, so if I've got sand in the water, what I need to do first is I need to filter it. And then if I want to remove the things that are dissolved in the water, then I can heat it. Okay, so those are different ways of separating mixtures. And I've got more ways to show you in just a minute. So the processes of separating mixtures. Processes to separate mixtures. We've got evaporation, condensation, magnetism, filtering, sieving, and decanting. And we're going to talk about those in just a minute. So what is evaporation and condensation? Well, this is essentially how we get rain. So the water cycle that we have in nature, this is how it works. You've got heat that hits the seawater or the lake, and then the water evaporates, and then it goes up in the sky. What happens up in the sky? It gets cold. So that gas or that seawater that's in gaseous form, steam or water vapor, is going to condensate and then fall back down onto the earth. And this time it's got no salt in it, so it's going to fall down as fresh water that collects either in underground reservoir or goes into lakes or streams or rivers and so on, right? So that is how that works. You've got heat, it goes up, and the solid remains behind and crystallizes while you can collect the gas. So that's called evaporation and condensation. So heat turns the water from liquid into gas, and then cooling the water turns it back to liquid. Okay? Heating the water makes it go from liquid to gas. Cooling the water makes it go from gas to liquid. Okay? Magnetism, we've talked about that. So using a magnet, you can separate the iron from the non-iron material, or the ferrous material from the non-ferrous material. It's not just iron, nickel as well as another example of a ferrous material. So you can separate things like copper nails and iron nails. Iron nails are attracted to magnets, while copper nails are not. So you can separate them using a magnet. Filtering, one of the most common ways of separation. If you want to separate two things, one of them is a solid, the other one is not, you can use a filter. Or if you want to separate things that are small compared to things that are slightly bigger, you can use a filter or a sieve in that case. Sieving. So sieving is when you separate two solids usually, and what you do is you have two separate sizes. So let's say you've got raisins mixed in with flour. So what I can do is I can get a sieve and I can separate the flour. The flour goes down while the raisins remain on top. or let's say for example lentil seeds are mixed in with some flour. What I can do is I can get the sieve, and the sieve can be used to separate the flour from the lentil seeds. Decanting is one of like what I call lazy separation. If I want to separate the oil from the water, what I can do is I can slowly pour it out. Now I'm not going to do that here because I've got my desk with my laptop and everything else. But what I can do is I can slowly pour it out, and that is a way of separating two liquids, for example, oil and water. The oil will remain behind, or the oil will pour out while the water will remain behind, and so on. So if I do it really slowly and carefully, I can separate the oil from the water, right? So back to this, we've already covered this. A solution is made up of solvent and solute, and I'll recover this when I'm doing the concept map at the end. Right, so what are the different types of solutes? Now we've talked about suspension, colloids, and solutions, right? 3 different types, right? So let's talk about solutions specifically. A solution is made of a solvent, like water, with a solute dissolved in it, like salt or sugar. Now, what is the difference between different solutes? Well, it turns out those solutes are compounds, right? So they're either ionic compounds or molecular compounds, also known as covalent compounds. So molecular compounds is just another fancy name for covalent solutes. So we've got covalent solutes and ionic solutes. And in short, basically, there are differences between them. And I'm not going to cover this in any great detail, besides saying that molecular compounds are made of things like sugar, okay? They don't break down into ions because it's not made of ions. Molecular compounds is made of nonmetals. So if you remember the formula for glucose, C6H12O6. Now, if you look at these are all nonmetals, which means they're not ions. They share electrons. It's a covalent compound. In covalent compounds, we share electrons. There's no give and take. There's no ions involved. So in this case, this here is a polar molecule, which means it's slightly charged. Remember when you're talking about polarity, polarity is when things become slightly positive or slightly negative. They have poles, like water, for example. We have H2O, we have oxygen and hydrogen, and although they share electrons, water is polar because the oxygen becomes slightly negative while the hydrogen becomes slightly positive, because the pull from the oxygen is more than the pull from the hydrogens. Now, because water is polar, and because this here is polar, they attract each other, and this distributes itself throughout the liquid and dissolves in the water. Okay? Now, that's not what happens in ionic solutions. With ionic solutes, what happens is this separates. Now, that compound, for example, sodium chloride, that compound becomes sodium ions and chloride ions. And basically, they spread throughout the solution as well, just the same way as molecular compounds do. But these ones will be attracted to the negative pole of the water, while these ones will be attracted to the positive pole of the water. Molecular compounds are different. Molecular compounds, the whole compound doesn't separate. And so it's held together with the water molecules using weak hydrogen bonds. You don't have to know about that. But with ionic solutes, the bonds are slightly stronger, and they break down into ions. Okay? So in conclusion, okay, just because I don't want to spend too much time on it, in molecular solutes, the molecules stay intact. So in molecular solutes, the molecules stay intact, and when they dissolve, they spread out evenly throughout the solvent. Okay? Whereas in ionic solutes, the ions separate and spread out individually into the solvent. And the ions are strongly attracted to the solvent because the water molecules are positive and negative, which pulls the ions apart. Whereas the molecular solutes are attracted to the solvent through weaker forces like hydrogen bonds. Okay, and that's as far as you need to know, really. In fact, that was probably a bit too much. That was probably a bit too much, to be honest. Right, concentration. Concentration just refers to when solutes are dissolved in solvents. That can result in things changing for the solution. How so? Well, let's take water for example. Water is known to boil at exactly 100 degrees Celsius. But if you add salt to water, turns out that changes the properties of the water. So it can start boiling, for example, instead of 100, it can boil at 102 degrees Celsius. So I can find out the purity of the water by boiling it. So if I take, for example, water from the sea or from a lake, let's not the sea, because the sea is quite obvious that it's not pure. But let's say if I take water from a lake and I boil it and it doesn't boil at exactly 100, then that means it's got stuff in it. It's got solutes dissolved in it. Not only that, it also freezes at different points. So rather than freezing at 0 degrees Celsius, it now freezes at -2, for example, or -1.8 degrees Celsius. So basically, when solutes are dissolved in water, they change the property of the water. And it's not just water. Any solute, any solvent that has solutes dissolved in it will change the properties of it, right? So the boiling point changes, the freezing point changes. And on top of that as well, water in its pure form, in its distilled form, doesn't conduct electricity very well at all. However, when you dissolve ions in water, when you dissolve ionic compounds or ionic solutes in water, like salt, then suddenly the water becomes conductive, right? And it starts conducting electricity. So the properties change depending on what solute is dissolved in the water. That's the point I want you to get out of this. Now, not only that, you've got concentration of different solutes in the solution. So for example, if I have a 100 ml solution with a 17 grams of salt in it, then that means 17% of it is salt, or the concentration of the salt in it is 17%. Now, what if I have, I'll give you a different example. What if I have a 500 ml solution and I've got 30 grams of sugar? What is the percentage? What is the concentration? Now, what you need to do here is divide the top by the bottom, the solute by the solvent. The solute by the solvent. So that's 30 divided by 500, which should hopefully give you 6%, or 6 out of 100 percentage-wise, right? And that's how you calculate that. Okay, so it's very, very easy to calculate the concentration. You just have to divide the solute by the solvent. I've got another example over here. So I've got the Baltic Sea, for example, is 4 times as salty. No, sorry, it's 4 times less salty than the Red Sea. The Red Sea has 40 grams of salt per 1,000 mils of water, whereas the Baltic Sea has 10 grams of salt per 1,000 mils of water. So basically, 4 times, the Red Sea is 4 times as salty as the Baltic Sea. Okay, and if you see PPT over here, that doesn't stand for PowerPoint, that stands for parts per thousand. So the Baltic Sea has 10 parts per thousand, whereas the Red Sea has 40 parts per thousand. Okay. And how does solubility change with temperature? Well, I think you guys know the answer to this. Basically, the hotter things are, generally speaking, the hotter the solvent is, the easier for things to dissolve in it. So if I take tea, for example, and I try to dissolve some sugar in it, obviously, if the tea is cold, then the sugar will take longer for it to dissolve. If I have iced coffee and I try to dissolve some sugar in it, it's going to take longer than if it was hot coffee. Hot coffee will make the tea dissolve a lot, the sugar dissolve a lot faster. And that's got to do with the collisions, right? But you don't have to worry about that at this stage. But generally speaking, if things are hotter, it helps the dissolving process. Solubility increases, solubility goes up as temperature goes up. If the temperature goes up, the solubility goes up. It's called a direct relationship. And how does pressure affect that? Well, let's look at pressure. So while pressure has little effect on the solubility of solids, it doesn't really affect solids so much. It does affect gases, right? So as you increase the pressure, the gases that dissolve, the gases dissolve easier in the liquid. And some of you might be a bit surprised by that. Well, hang on. Do gases dissolve in liquids? Absolutely. Think of a can of fizzy drink, okay, a can of soda. Now, that can of soda has gas dissolved in it, carbon dioxide mainly. It's dissolved in the juice or in the soft drink. And so when you open it, what happens? The pressure is released and therefore the gas can now escape, right? So it's easier to have gas dissolve in high pressure. High pressure causes the gas to dissolve much faster than low pressure. Okay? That's all I want you to know about that there. And okay, let's do the concept map now. Okay, so all matter, everything is either pure substance or mixture. If it's a pure substance, it can either be an element, like gold, for example, or it can be a compound, like water or carbon dioxide. They're both pure substances, but they are compounds. Now, as far as mixtures are concerned, they can either be homogeneous or they can be heterogeneous. Homogeneous mixtures are things like this vinegar, apple juice, salt with water. Okay, they are clear solutions. And solutions are clear. You can see through them. They're transparent. Solutions are made from two things. Those are solute, which is the solid, and solvent, which is the liquid. Usually water. That's why water is called the universal solvent, because many things dissolve in it. And solutions, so solute, solvent, and they can either be molecular, which is another word for covalent, sorry about my handwriting, it's so hard to write on glass, or ionic. Okay? Things like salt. Well, that's like sugar. What about heterogeneous? Heterogeneous can either be a colloid. Now, some of you might be wondering, well, hang on a minute. Colloid, you said that's heterogeneous. Yeah, so like for example, lentil soup, it's made of onions and whatever, and even if you blend it, if you leave it for a while, things separate. So it's actually heterogeneous. But, and if you look carefully with a microscope or with a magnifying lens, you can see that it's heterogeneous. There are different things in there. But some things are kind of in between. So for example, skim milk is homogeneous. It's not heterogeneous, even though it is a colloid. So just because it says colloid and it's under heterogeneous, colloids can sort of be homogeneous as well. Okay, can sometimes. So that's why I've got that kind of faint dotted line there. So colloids, things like milk, it is uniform throughout but doesn't allow light to pass through. And then we've got suspension. So things like oil and water. Okay, or sand and water, or things like that. Okay, boys, I hope that was clear. That's all for this week. I know it's a lot of stuff. Sorry, I know it's kind of like rushed, but the good thing about videos is you can pause them, you can rewatch them, you can pause them again and rewatch them again, and you can watch them in bed even if you want to. So drink a bit of tea, a bit of solution, a solution of tea, and enjoy watching the video. Okay, adios, over and out. I'll catch you later. Ciao.